Hello everybody, welcome back to another glorious maths video. In this video we're going to be looking at field extensions, and this should be a pretty concise video covering all of the important details. And there's a little link to polynomial rings that I'll include at the end because, well, we looked at those last time. So, let's get right into the video. So first of all, I'll begin with the definition of the thing we're going to be studying today. So that is, if K subset of F is a subring of F, subfield, so that means that it's a subring and it's a field as well. So if K, a subset of F, is a subfield of F, that is, it's a subring of F, but it's also a field, then we say that F is as an extension field over K, and write something like this. So this literally just means, it's just a concise way of writing that K is a subfield of F. But it's important, this is an important notion. So, something to spot is that actually, it's very fascinating, actually F is a K vector space. And, well, verification is quite easy, but this is quite useful. For example, we can say the dimension of F as a K vector space, and indeed we do. We say that we denote by this the dimension of F as a K vector space. So, for example, the degree of the rational this is equal to 2 because the basis of this ring right here, the set of all a plus b square root of 2 where a and b are rational numbers, is just going to be 1 square root of 2. This is literally going to be the basis. And so that's quite an interesting thing. And actually there's a theorem with a proof which you can find in pretty much anywhere, so I won't include it, but it's quite an important theorem, and I won't prove it, proof is quite long and you can find it at many places. You can find it in many places, so I think it's called the Tower Law. Tower Law. And what it says is, if we have F, I'm not sure if this notation is allowed, but it's much more concise anyway. That is, K is a subring of E, which is a subring of F. And I think that E is called an intermediate field. And if the degree of, so the dimension of F as an E vector space is finite, and these two are finite, then we have that the degree of F over K is equal to the degree of F over E times the degree of E over K. And that's quite a very neat proof, which might actually agree with our intuition. If we have an intermediate field, then the dimension kind of gets lost, you could say, when you multiply them together. But yeah, okay, so this is the these are the basic definitions and theorems. I'm trying to give it as concise as oh god. Sorry. Now I'm gonna connect it with polynomial rings. So I'm trying to make this video as short, like not as short, but like as concise as possible, whilst still giving the key definitions for this. I'm not going into so much detail, but giving key definitions so that it's perfect length. So yeah, I'm gonna finish with a nice link to polynomial rings. So, first of all, definition. We might be familiar with this definition from, again, our studies of polynomials, but just with real or maybe even complex coefficients, but this is a more general version. We say that x, which is in a field K, is algebraic if there exists a p not equal to 0, a polynomial in the polynomial, in the ring of polynomials with coefficients in x, such that p is not equal to 0, so it's not the zero polynomial, such that x is the root of p. So, basically, if x is the root of any polynomial with coefficients in k, and it's not a zero polynomial, then x is called algebraic over k. And if it's not algebraic, x isn't algebraic over k, it's transcendental. So, we have these two definitions. So this is already a nice tie into polynomial rings. And now, using this and a further definition, we have a nice link between transcendental numbers, this definition I'm about to give, and polynomial rings. So, we denote by k of u, where k is the subring of f, the smallest subfield of f containing k and u. Alright, now we can proceed. So, theorem. If u in k is transcendental over f, if u in f is transcendental over k, then k of u, so the smallest subfield of f containing k and u, is actually isomorphic to the polynomial ring k of x. Well, that's quite an interesting result. It's not the result that which would spring to mind. Perhaps if u were algebraic, then this might make a little bit more sense, but no, it's different. It's if u is transcendental, then the smallest subfield of f containing u and k is actually isomorphic to the polynomial, so the ring of polynomials with coefficients in k. Fascinating. So let's prove it. I haven't used red, this board, side of the board. So, proof. And it actually follows from the first isomorphism theorem for rings. So, clearly, since U is transcendental, of course over K, okay, over K, then G of U is not equal to 0 for all G in the polynomial rings like that. Therefore, we can define phi tilde sub u from k of x to k of u by mapping. It maps f over g to f over g of u. Sorry, I'll write that more clearly. F of u over g of u. And clearly this is well defined for all g not equal to 0. Since since this is never going to be 0 because u is transcendental. Now, since phi twiddle this homomorphism isn't trivial, it's injective or a monomorphism. So an injective homomorphism is called a monomorphism. Okay? Now, therefore, by the first isomorphism theorem, k of x is isomorphic to k like this. Ta-da! And yeah, that's about everything I have today, and I'll see you in the next video.